Now we will see the design of a helical spring. So here in this diagram you can see the diagram and the various terms which are related to that particular diagram. So we will see the capital D is the mean diameter of the spring coil. In this diagram you can see here is capital D, then small d is the diameter of spring wire, small n is the number of active coils, where capital G is the modulus of rigidity for spring material, where W is the axial load on the spring, tau is the maximum shear stress induced in the wire, where capital C is the spring index, where P is the pitch of the spring, and delta is the axial deflection of the spring. So all these terms we have already seen in earlier video. Now we will see it one by one how to design the particular helical spring. So now the applied axial load produces the twisting moment in the spring wire while compression of the spring. Hence torsional shear stress induced in the spring wire is equal to T is equal to W into D by 2, where W is the axial load, where capital D is the mean diameter of the spring coil. So now T is equal to pi by 16 into tau 1 into d cube is equal to W into D by 2, where tau 1 is equal to 8 into W into D divided by pi d cube. So by rearranging the term, finally we will get the stress induced in the spring is equal to 8 into dw 8 into WD divided by pi d cube. So in addition to the torsional shear stresses, the direct shear stresses are also induced in the spring due to the applied axial load W. So the tau 2 is equal to load upon cross sectional area, where tau 2 is equal to W upon pi by 4 d square, where cross sectional area of that particular wire is pi by 4 d square. So tau 2 is equal to 4 into W divided by pi d square. So from above equation we can also determine the resultant shear stress without considering the effect of curvature on the stresses. So tau 1 is equal to tau 1 plus tau 2, where tau is equal to 8 into WD divided by pi d cube plus 4 into W divided by pi d square. So by rearranging the term, we will get 8 WD divided by pi d cube into 1 plus d upon 2d. So tau is equal to 8 into WD divided by pi d cube into 1 plus 1 upon 2c, as c is equal nothing but capital D by small d. So by considering the earlier equation, that is spring index, and final equation we will get, that is resultant shear stress tau is equal to Ks into 8WD divided pi d cube, where Ks is nothing but shear stress factor. So when stress due to the curvature of the wire is to be considered, the shear stress becomes tau is equal to K into 8 into W into D divided by pi d cube, where K is the wall stress correction factor. So what is K? Where K is equal to 4C minus 1 divided by 4C minus 4 plus 0.615 by C. So what is wall corrections factor? In the design of a helical compression spring, the determined shear stress are without considering the effect of curvature of the spring. So that particular equation we will got first, tau is equal to Ks into 8 into WD by pi d cube, is without considering the effect of curvature. But these stresses are induced in the spring due to the application of the axial load W on the spring only. So while manufacturing of the helical compression spring, the spring wire is to be bent in the helical coil, and this curvature increases the stress on inside of the spring and at the same time decreases the stress on outside of the spring. So thus the length of the inner fiber is less than the length of the outer fiber. So this result in a stress concentration at inside fiber of the coil, and this curvature effect is to be considered larger for higher values of the spring index. So hence wall correction factor is to be introduced in the stress equation. So tau is equal to K into 8 into WD divided by pi d cube. So instead of K, here we have to use KW, that is wall stress correction factor, that we need to consider the shear stress due to the effect of curvature. So now K is nothing but the wall stress correction factor, where K is equal to, we can find out that wall stress correction factor by formula 4C minus 1 divided by 4C minus 4 plus 0.615 by C, where C is the spring index that we can find out capital D by small d, where wall correction factor may also be considered as composed of two sub factors as shear stress factor and stress concentration factor due to wire curvature. So K is equal to Ks into Kc, where Ks is the shear stress factor and Kc is the stress concentration factor. Now here in this table, the spring index C and the wall stress factor, if your C value is 3, 4, 5, 6, 7 and up to 10, in that case you need to consider wall stress factor likewise. Or in case of an exam, in problem statement they will gives you that spring index table and the wall stress factor. So whatever the C value you will get, you need to take that particular wall stress factor. So there is no need to remember this table. Now the deflection of helical compression spring. So the axial deflection of the spring can be determined, that is delta is equal to theta into d by 2, that is deflection into radius. So from torsion equation, we already know that torsion equation, it is T by J is equal to G into theta by L, where theta is equal to T into L divided by J into G by rearranging the term. Now we know that T is equal to W into D by 2, that is torque is equal to applied load into radius, where length is L is equal to pi into D into N, where J is equal to pi by 32 into d raised to 4 because of it is circular one. So by torsion equation, now we will put all this value in above equation in theta equation, where theta is equal to D is nothing but W into D by 2 into L is nothing but pi into D into N divided by G into, where J is the pi by 32 into d raised to 4. So finally we will get theta is equal to, that is axial deflection, you can say theta is equal to 16 into W into D square into N divided by GD raised to 4. Now by axial deflection equation, delta is equal to 16 into W into D square N by GD raised to 4 into D by 2, where rearranging the term, so final equation will get delta is equal to 8W C cube into N divided by G into N. So deflection per active turn can also be determined, divided, that is delta by N is equal to 8W C cube divided by GD, just only rearranging the term. Now next term, the energy stored in a helical spring of a circular wire. Here is delta versus W graph is shown. So the energy is not stored in a spring material beyond the elastic limit. There will be a straight line of a load and deflection. So the energy stored in a spring is U is equal to 1 by 2 into W into delta. Now the maximum shear stress induced in the spring is what? Q is equal to K into 8 into WD divided by pi d cube, where W is equal to pi q d cube divided by 8 into kd. So deflection of the spring is what? Delta is equal to 8 into W, earlier equation, 8 into W and d cube by GD raised to 4. So from equation of the energy stored in spring, we can put that W value in that particular equation. So you will get U is equal to 1 by 2, that pi q d cube divided by 8 kd into 8W and d cube by GD raised to 4. So again put the equation of W in above equation, and finally you will get the U is equal to Q square divided by 4g k square into V. As this unit is contains more formulas, so you need to remember this formula to solve the problem. Now here again V is the volume of the spring wire, where V, how to find out volume, that is pi dn into pi by 4 d square. So when the load P falls on a spring through height h, then the energy absorbed in the spring is U is equal to P h plus delta, where 1 by 2 into W into delta, where W is what? Equivalent static load, that is gradually applied load which shall produces the same effect as by the falling load P, and delta is what? Axial deflection produced in the spring. Now the next term, the springs are in a series and springs are in a parallel. When springs are in a series means S1 and S2, these two springs are connected in a series, you can say, and springs in a parallel, that S1 and S2 springs are connected in a parallel, where W is applied load, where at the downward side, at the downside it is grounded one. So when, now just we will see the springs in a series. What is it? When the springs are connected in a series, then total deflection produced by the spring is equal to the sum of the deflection of the individual spring. Now we will see the equation, how the equation will come in picture for the springs in a series, where W is the load carried by the spring, delta 1 is the deflection of the spring 1, delta 2 is the deflection of the spring 2, where S1 is the stiffness of the spring 1 and it is calculated by W by delta 1, where S2 is the stiffness of the spring 2, where it is calculated by W upon delta 2, where delta is equal to, it is the addition of the two deflection of the each spring, that is delta 1 plus delta 2, where delta is equal to W upon S is equal to W upon S1 plus W upon S2, where just W will get cancelled, so 1 upon S is equal to 1 upon S1 plus 1 upon S2, where S1 and S2 are the stiffness of the spring 1 and spring 2. Now when the springs are in a parallel, so what will happen when springs are connected in a parallel, then the total deflection produced by the spring is same as the deflection of the individual spring, that is delta 1 is equal to delta 1 plus is equal to delta 1 is equal to delta 2. So the load shared by both spring will be what? W is equal to W1 plus W2. Then W means what? It is delta into S, and W1 is delta 1 S1, W2 is delta 2 S2. So delta is the same, as you know that delta is equal to delta 1 is equal to delta 2. So these terms will get it cancelled. So S is equal to S1 plus S2, where W is what? Load carried by the spring. Delta 1 is the deflection of spring 1, delta 2 is the deflection of the spring 2, where S1 is the stiffness of spring 1, and which can be calculated by W1 by delta 1. S2 is the stiffness of spring 2, which is equal to W2 by delta 2, where W1 is the load shared by spring 1 and W2 is the load shared by the spring 2. Now the next term, the buckling of the compression spring. Now in this diagram also you can see how the spring will get buckled. Experimentally it is found that when free length of the spring is more than 4 times the mean or pitch diameter, then spring behaves like a column and may fail by buckling at a comparatively low load. So the critical axial load that causes the buckling in a spring is WCR is equal to S into KB into LF. So by using that formula you can find out buckling in the spring, where S is what? Spring rate or the stiffness, and it is calculated by W upon delta, where LF is the free length of the spring, already we have seen LF. Then KB is what? The buckling factor, and it is calculated by LF upon D. Now the theoretical part, now the methods to avoid the tendency of buckling of the compressive spring. How we can avoid the buckling of that particular spring? To avoid the tendency of the buckling of the spring may mounted on a central rod or in a tube, and when spring is located in the tube, then the clearance between the tube walls and the spring should be kept as small as possible to allow for increase in a diameter in the compression of the spring. So now next term, very important, surge in a spring. What is surge? When one end of the spring is resting on the rigid surface and a load is suddenly applied on the other end, then all the coils of the spring will not suddenly deflect equally. So some time is required to propagate then the stresses along the coil of the spring. So in this case, the coil in contact with the suddenly applied load takes up whole deflection and then transmits a large part of the deflection to the adjacent coil, and this will create the resonance in the spring. So this result in a very large deflection of the coil and correspondingly very high stresses, and this causes the failure of entire spring, and this phenomenon is called as the surge in a spring. So the resonance will takes place in that particular spring, and when the resonance will takes place, the whole spring may get permanently fail, and there will be the what you can say the large deflection and correspondingly very high stress, and this causes the total failure of the spring, and that particular phenomenon is called as a surge of the spring. Now what are the methods to avoid that surge in a spring? So by using the spring of a high natural frequency, so to avoid the resonance you need to use the spring of a high natural frequency. Now the second one, by using the friction damper on the center coil, and third one, by using the spring having pitch of a coil near the ends different than at the center to have different natural frequency. So these three methods you can use to avoid the surge in a spring. Now we will see the next part, that is lip spring. Now generally you have seen that lip spring, it is generally used in heavy duty vehicles to support the load. Now we will see what is lip spring. A lip spring is of a semi-elliptical form and consists of a number of leaves. The longest leaf is called as a master leaf and has its ends formed in the shape of an eye through which bolts are passed to secure the spring to its supports. Now the other leaves are also called as a graduated leaves, which are arranged in the order of decreasing length and then clamped to the master leaf with the help of a strips. In the diagram you can also see that there is a center bolt, then spring eye on the both sides, and there are graduated leaves and full length leaf. Now since master leaf has to withstand vertical bending load as well as load due to the sideways of a vehicle. Therefore, due to the presence of stresses caused by these loads, it is usual to provide two full length leaves and rest as graduated leaves. So there are two full length leaves and other rest are graduated leaves. Now we'll see one by one various terms. That is, first one is center bolt. You can see in this diagram also a bolt which is used to hold the leaves together is called as a center bolt. The second one, U clamp. U clamp also you can see in the diagram. It is used to clamp. A clamp is used to clamp the spring with the axle. Then third one, rebound clips. They are located at the intermediate position in the length of the spring so that the graduated leaves can also share the stresses induced in the full length leaves when the springs rebounds. Then the fourth one, the camber. The leaves are initially given curvature so that they will tend to straighten under the action of lead, and this is called as a camber. So this is about the leaf spring. Now what are the materials which are used for the leaf spring? Now oil hardened and tempered alloy steel such as 50 CR1, 50 CR1 V23, 55 USI2, MN90. So these are the various materials basically used for the manufacturing of the leaf spring. Now what are the advantages and the applications? The advantage is that leaf spring acts as a structural member rather than energy absorbing device, and again leaf spring can take up the lateral loads, brake torques and driving torque in addition to the shock. And the applications of the leaf spring are, they are generally used in automobile like heavy loaded trucks, as already I have told you, in jeeps, trailers, etc., and in machines to absorb the shock loads. Thanks a lot for listening carefully. Here is the end of the unit number 6.